Now we want to introduce the number e. This was first used by Euler several hundred years ago. We already know that ln(x) is defined using the integral. It has range from negative infinity to infinity and strictly increasing. So therefore, there has to be a number so that ln of that number is equal to 1. Now that number, that special number, we're going to use letter E to represent that. It is a positive real number, so that ln of this number is equal to 1. Geometrically speaking, this number E is a number so that the area of the region bounded by the 1 over t, so bounded by this function, on this region 1 to E is 1. So the E is the number so that this area is equal to 1. Now, so the next thing is to search for, to figure out what this number is, right? One thing is it has to be in between 2 to 3. So this actually should be a pretty fun thing for you to prove that it is between 2 to 3. Actually the number, specific number, it's an irrational number. The value, numerical value is about, numerical value is 2.72, okay, but 2.718, 28, 18, 28, 1828, 1828. Sorry about the mistake there. 1828 and 46 and so on and so forth. It's a rational number. So again, it can be proved pretty straightforward using some knowledge that you have mastered before. So let's prove that ln2, which means the area from 1 to 2, right? So ln2 is actually less than 1, okay, less than 1, so that the E has to be greater than 2. That means, okay, ln2 is less than 1. So let's find the Riemann sum using two subintervals. That means this value is 1.5, which means 3/2, right? 3 over 2, 3/2. And let's construct two Riemann rectangles using the left point. So the height of the first rectangle is going to be 1. The height of the second rectangle will be 1 over, because this function is 1 over t, so it's 1 over 3/2, which means 2/3. So the next height is 2/3. So this ln2, which means the area bounded by the curve, is definitely less than the sum of these two rectangle areas. So therefore we can see that less than the area of the first rectangle is going to be 1 times 0.5, I'm sorry, 1/2, because the width is 1/2, right? The width of the rectangle is 1/2. And the second one is the height is 2/3 times 1/2. And if you see that this is 1/2, this is 1/3, 1/2 plus 1/3, which is 5/6. So which is less than 1. So ln2 is definitely less than 1. So it's not 1 yet. So therefore the E has to be further to the right, right? Because ln E has to be 1. And now you can actually use the, you can show, okay, maybe one little assignment after class exercise, maybe when you have spare time, so try to show that this ln3, so show ln3 is actually greater than 1, okay, actually greater than 1. So here you want to show that, choose a appropriate number of subintervals, and then show that the area of those Riemann rectangles is greater than 1, so that ln3 is greater than 1. So it takes a little try and error, but I can tell you that if you use n equals 7 or 8 subintervals, you can actually show that ln3 is actually greater than 1. therefore this E is definitely in between 2 to 3, okay, 2 to 3, because ln2 is less than 1, ln3 is greater than 1. So therefore, in order for ln to be 1, this E has to be in between 2 and 3. And in fact, this is the value of the E. Now, ln e to the n is equal to n times ln e, because n can be moved to the front of the ln. And ln e, by definition, this is 1, so therefore this is n. So using some nice convenient points, and which means the power of e, okay? And then we can actually plot the graph so that we make a more accurate graph. And it looks like this. So natural log is a slow growing function. Even though when x is approaching infinity, the y value is approaching infinity, it has the rate of increase is pretty slow, okay, very slow. Now let's talk about a graph of some log functions using the transformation, okay, using the transformation. So let's take a look at how can we graph this function. So I can see that there's a negative number in front of the function ln. So I can this negative sign tells me, okay, this 2 is a vertical stretch by a factor of 2. This negative means reflection about the x-axis, right? So therefore, so I'm going to make a very rough sketch. Doesn't mean to be accurate, but try to reflect the idea of using the transformation to make a sketch. So this negative 2 means, just think about negative 2 of f of x, right? So it's a vertical stretch by a by factor of 2, and then flip, right? Flip across the x-axis. So now I'm gonna begin with lnx. So say this is my lnx. This is gonna be 1. And when you do a vertical stretch, it becomes, so vertical stretch by 2. If this, then it should be double. The height should be double. Here, the height should be double. So basically, when you, similarly on the bottom, you double it, right? So this will be 2 times the lnx, okay? And the negative, you're gonna flip it. So therefore, I'm gonna say flip the black curve with respect to the x-axis. So therefore, this will be negative 2 lnx. Now finally, this over 3 inside here, over 3, just quickly remind you that so f of x over 3, this means horizontal stretch by factor of 3, actually, factor of 3. Of course, we still have in the front, there's a negative 2. So we actually will do a horizontal stretch on this green line. Green line is the negative 2 of lnx, okay? So that means everything you just need to multiply by 3. So so therefore, when this is 1, this becomes 3, right? So if this is 1, then it becomes 3. And if this were, say, 2, then it becomes 6 further out. So that the graph will be quite a bit of stretch. So basically, it will be something like that, okay? So this will be negative 2 ln x over 3. Now let's take a look at another one. The second one is much easier. So this can be considered as f of x plus 2, where f of x is the ln x. and this x minus 2, that means you simply shift the ln x to the left 2 units. So therefore, if this is the ln x, suppose this is the ln x, and this is 1. When you shift that to the left 2 units, so 1, 2, this becomes negative 1. Everything just, and the vertical asymptote here, that's actually negative 2 is the vertical asymptote. It won't cross the x equals negative 2. All right, so some quick comments on doing the graph. Now let's take a look at the calculus of natural logarithmic functions. First of all, the derivative. So derivative ln x is 1 over x when x is greater than 0. This is coming from the definition because ln x is antiderivative of 1 over t, right? So therefore derivative is just 1 over x. And the chain rules, if u is a function of ln x, then the derivative will be, so the derivative will be, so if we have ln u, right? So if y is equal to ln u, and so the derivative will be 1 over the u times the derivative of the inner, which is u prime, which becomes u prime over u. Now, this actually can be extended. So when the derivative of absolute value of x is actually equal to 1 over x, this can be seen by when x is greater than 0, the absolute value of ln x is just the same as x. And therefore, derivative of ln, in that case, the derivative, the ln absolute value of x will be just ln x. So the derivative of that will be just the same as 1 over x, which is 1 over x. Now when x is less than 0, absolute value of x is equal to negative x. So now ln absolute value of x becomes ln of negative x. So when you find the derivative of ln absolute value of x, you find the derivative of ln negative x. And the derivative, so the derivative according to the chain rule now, right? So it's going to be the derivative of the u, this is your u, derivative of negative x will be negative 1. And of course, over the u, right? We are using this property here, over the u, which is negative x, so which is 1 over x. Therefore, regardless the sign of x, the ln of absolute value of x, the derivative is 1 over x. So this is similarly, very similar, right? Okay, now let's apply these rules to the following derivative. Again, please pause the video and give a try yourself first, and then let's compare the answer. So here, the u is the 3x. So f prime of x will be the u prime over u, or some people probably use the chain rule without even considering this as a formula, which will involve like 1 over the u times the derivative of the inner function, right? So some people tend to do that. Either way is fine. So here, u prime will be just 3. U will be just 3x, so which actually is 1 over x. Now the second one, the u is x squared plus 4. So f prime of x will be, again, u prime over u. Probably in the future you can skip writing that now once you feel comfortable with that. So u prime will be 2x. The derivative of 4 is just 0. And the u is x squared plus 4. Okay, so next. Now, the problem number 3, we have a product of two functions. So a product rule will be involved. So f of x, the derivative of f of x will be the derivative of the first function times ln x, the second function, plus the first function times the derivative of the second function, which is equal to a derivative of x, just 1, times ln x, which is just ln x, plus x times derivative of ln x is 1 over x, and they cancel out, and therefore we have ln x plus 1. Next, in this case, my u is actually the secant x, not the absolute value of secant x, only secant x. So the f prime of x will be the derivative of the u. So let's write this very clear, not this guy, okay? So not this one, but this one. So according to the chain rule, the derivative of the secant, which is secant tangent, and the over the u, which is secant, and secant cancel, and we're left with tangent x. All right, the last one, we have a nested functions. We see that most inner one, let's call it, say, w, is actually the x squared. This is the most inner function, right? And the middle one, let's call it u. U is just ln x squared, which is the ln of the w. And the outer function y is actually equal to ln of the u, right? So this is the ln x squared, which is the ln of the u. Now the derivative of the function, you just multiply the derivative of the outermost times the derivative of the middle one times the derivative of the innermost. So therefore the outermost will be 1 over the u, right? If you feel comfortable to replace the u with ln x squared, go ahead do that, times the derivative of the middle one, which is 1 over the w, right? W times the derivative of the innermost one, so times the dw, well, basically we can just write it out now, which is the 2x. So therefore, eventually, this is what we have, 1 over u, which is ln x squared, times 1 over w, which is the 1 over x squared, times 2x. And simplify if possible, so cancel an x, we have x left. And finally, we have 2 over x ln x squared. Now, please, you have to be very careful. I would not do, so let me scroll up a little. So it will be incorrect to do the following. So some students may think about, okay, let's move these exponents to the front, right? To the front. So therefore it becomes 2 times x ln x, and cancel the 2. Please don't do that. Don't do that. If you do that, here this x can be negative. However, here if you write that, this x has to be positive. So they're no longer equivalent actually. So therefore, this should not be done. Now let's continue to the next problem. Sometimes log properties can be used to simplify the problems like those. So if you use the chain rule without simplifying, you can see that derivative of the ln u and the derivative of this u can be a little complicated, right? So now you can actually simplify, expand it. Think of this as ln x minus 1 over x, and this is going to be 1/2, right? And then pull the 1/2 these exponents to the front, and then you have a quotient. The quotient becomes the difference of the two logs. Okay, now we actually prefer to differentiate this expression rather than this expression. So now f prime of x equals 1/2 times 1 over x minus 1. The derivative of x minus 1 is just 1, so 1 here, minus 1 over x. So usually this is acceptable to me, but of course, if you want to continue to simplify it, combine it, feel free to do so. So x minus 1, x times x. So you have to multiply this by x over x, multiply the second one by x minus 1 over x minus 1. So therefore you have x minus x plus 1, and these two x cancel. So finally you have 1 over 2 times x times x minus 1. This is a little more simplified, but again I'm fine with this actually, because we are focusing on finding the derivative. All right, the next one, because we see a product here, so we are going to expand it. Instead of using the chain rule and then product rule for the inside function, we can actually write a sum of those, right? So ln x squared minus 1. Well, this is supposed to be power exponents 1/2, but this 1/2 can be pulled to the front. So let's write it into the front. Okay, finally, we are able to find this derivative, which is 1 over x plus 1/2. And this is your u. So here the u prime will be 2x over the u, which is x squared minus 1. And finally, these two cancel. We have 1 over x plus x over x squared minus 1. And again, this is completely fine. Now, lastly, we're going to look at one really nice application which is called the logarithmic differentiation, related to by taking advantage of the log properties. So if you have a complicated function that involves products, quotient, or powers, like this one, for instance, this one, it will be very tedious if you use the quotient rule, and because inside the quotient rule you will have to apply chain rule inside that you will have to apply inside the quotient rule there's a product rule, right? And then inside the product rule there's a chain rule, so you can imagine that it will be a little tedious. Now if you take advantage of the log property, this actually can be done much easier. So here's the suggestion. Step 1, take natural log to both sides. So in other words, apply the natural log to both sides. Okay, and then after you apply the natural log, you can write these products, quotient, and exponents into sum and difference of the single log expressions. So let's go ahead to that. So the left side is just simply the ln y, right? ln y. And take a look at the right hand side. So again, terms in the numerators, it will carry the positive sign. The terms from the denominator, it will have a negative sign. So therefore the right hand side becomes ln x cubed minus 1. And this exponent 4 can be written in the front. The next one will be positive sign, and the square root becomes exponents 1/2, which can be pulled to the front. So ln 3x minus 1. And the numerator that carries the negative sign, minus ln of x squared plus 4. So you can see that the original complicated looking function becomes just a sum of those individual log terms, right? So now we differentiate both sides. When you the left side, according to the chain rule, it will be y prime over y. The right hand side, you just differentiate each individually using the chain rule. So 4 times the derivative of x cubed minus 1, which is 3x squared, over x cubed minus 1, plus 1/2 times derivative of the 3x minus 1, which is 3, over 3x minus 1, minus derivative of the x squared plus 4 is 2x, over x squared plus 4. Now keep in mind, what do we want to solve? We want to find the derivative of the y. So you need to solve for y prime by multiplying both sides by a y. So let's do that. So therefore y prime equals y times, right? Y times. Now you can see that simplify each a little bit. 12x squared, x cubed minus 1 plus 3 over 2 times 3x minus 1 minus 2x over x squared plus 4. Now usually this is not considered as the simplified version. You want to substitute y. What is y? Y is the function given, so you want to plug this into the replace y with the given expression, right? So basically you want to plug in the y. So therefore finally this is what you are gonna answer, which is x cubed minus 1 to the power 4th square root of 3x minus 1 over x squared plus 4 times this whole expression. And this is it. Okay, so this is pretty much what we discussed in this section.